Morning. Am I audible? Is there any disturbance? Is there any disturbance? Please inform. Is there any disturbance? Yes, sir. Disturbance is there, or is my voice clear? Okay, I will start the class. So I'm going to discuss few more problems on Nyquist stability criteria, so that the concept, the stability analysis is more critical here to analyze and to know the stability condition of the system. That's why I thought let me solve few more problems. If my screen is not syncing with my audio, please inform. Okay then. So in this problem, we have to sketch the Nyquist plot. We have to sketch the Nyquist plot for the open loop. We have to sketch the Nyquist plot for the open loop transfer function. The given open loop transfer function is g of s h of s. That is equal to k into 1 plus 0.5s k into 1 plus 0.5s into 1 plus 5 by 1 plus 10s into s minus 1. So determine the range of values of k for which system is stable. So we have to determine for what range of k. So there is no specific value. There is no need to determine a specific value for k for the system to be stable. So within certain limits of k, within some lower value k, high value of k, within those limits, we have to check whether the system is stable or not. Okay, so we have to give the range of the k values. So if the k is lying between those range, then the system is said to be stable. So write down the question. Okay then. So given overloop transfer function is g of s h of s, that is k into 1 plus 0.5 s into 1 plus s by 1 plus 10s into s minus 1. Okay. So if you carefully observe in the denominator, there is no pole at the origin. Okay. So there is no pole at the origin. By looking at this denominator, we can say. So there is no pole lying at the origin. That means the Nyquist contour will lie at the entire right half side of your S-plane. So the Nyquist contour, it will occupy the right half side of your S-plane. It will have only 3 sections. So this is our Nyquist contour. Since there are no poles lying at the origin, or there are no singular points, that's why this is our contour. So draw this contour. Okay. So here we can see Nyquist contour has 3 sections. C1 section, there is my cursor, this is it. C1 section, C2 section, and C3 section. There are 3 sections in Nyquist contour. So here mapping of each section is performed separately. We are going to map each section separately, and overall Nyquist plot is obtained by combining all the individual section plots. Okay. So let us start with mapping of section C1. So I hope you people have drawn this in your notes. Let us move forward. Okay, so let us start with section mapping of section C1. Write it down. So we know in section C1, omega varies from where? From 0 to plus infinity. Okay. So first of all, let us consider g of s h of s. So what is our g of s h of s? It is k into 1 plus 0.5s by, I'm sorry, k into 1 plus 0.5s into 1 plus s by 1 plus 10s into s minus 1. Now replace s by j omega. If we replace s by j omega, so our g of s h of s will become g of j omega into h of j omega equal to k into 1 plus 0.5 j omega into 1 plus j omega into 1 plus 10 j omega into j omega minus 1. Okay, this is what we will get. Just write it down. Just replace the s with j omega and write down g of j omega and h of j omega equation. So if you, I don't know whether people have noticed or not. So here we have s minus 1 term, which is not in the form of 1 plus st form, but I didn't modify it because I'm going to solve this problem in a bit different pattern, not similar to the previous problems that we have discussed. Don't write theory, just write down the equations. If you complete, just mention in the chat box so that I can proceed. There is any disturbance, just inform. Okay then, now what I have done, if you carefully observe, what did I do in the next slide? So simply I have multiplied this 1 plus 0.5 j omega into 1 plus j omega, and I have multiplied 1 plus 10 j omega into j omega minus 1. See here, that's what I have done. I have simply multiplied the numerator terms and denominator terms. So simply I have multiplied. So this is what you will get. Okay. So after multiplication, so you can separate the real terms and imaginary terms. In this equation, the real terms are 1 plus k is constant. So 1 minus 0.5 omega square is our real part in the above in the numerator, and the imaginary part is 1.5 omega. Okay, that is our imaginary part. In the denominator also, real part is minus of 1 plus 10 omega square, and imaginary part is 9 omega. So simply what we have to do? We have to replace s by j omega in g of s h of s equation, and after replacing s by j omega, you multiply the numerator factors and the denominator factors. After multiplication, just write the real values aside, and just separate the real values and imaginary values. So write all the imaginary values on one side and the real values on the other side. Just segregate them and write down this equation. Okay, so you'll get this equation. So write it down, and later, so see, I wanted to further simplify this equation. That's why what I have done is I have multiplied and divided with this denominator to this equation. In this g of j omega, h of j omega, what I have done is I have multiplied the denominator with the numerator as well as with the denominator. So if you multiply and divide, you will get the next equation, that is minus k into 1 minus 0.5 omega square into 1 plus 10 omega square minus 13.5 omega square k plus j into 9 omega k into 1 minus 0.5 omega square minus 1.5 omega k into 1 plus 10 omega square whole divided by 1 plus 10 omega square whole square minus 9 omega whole square. So these sort of simplifications you might have been doing in your mathematical subject, but this today we are implementing in our control system. Write it down. Okay then, I hope you have written. So if people are not mentioning in the chat box, if you mention in the chat box, I'll be knowing whether you have completed or not. If you have completed, mention in the chat box. If you have completed, mention in the chat box. So that I'll be knowing that you are following the class. If you won't mention, how can I come to know that you are following or not? Okay, then simply nothing technical. Only we have simplified the equation. We have divided and multiplied the numerator and denominator with the denominator term. Now, so if you observe here, I will expand this equation. So if you observe here, there is a real part. This is our real part in the above equation. This is our imaginary part. And denominator, you can split it with respect to the numerator real value. You can write it down below the numerator real value, below the real value of the numerator and below the imaginary value of the numerator. Okay, so you can do that. So you can split it. Now, let us go to the polar plot. I will draw the, there is my cursor here. So if you draw the polar plot, this is our polar plot, as I have already explained. So this is our real axis, and this is my imaginary axis. So if this is my polar plot, this polar plot crosses the negative real axis at this instant. So whenever the polar plot crosses the negative real axis, so what is happening when it crosses the negative real axis? Definitely the imaginary terms will become 0. Okay. So the frequency at which these imaginary terms are becoming 0. So that frequency is known as, that frequency is known as phase crossover frequency. Okay, that frequency is known as phase crossover frequency. At phase crossover frequency, the polar plot crosses the real axis. Okay, similarly, the locus of g of j omega, h of j omega will cross the real axis. Okay, so when it crosses the real axis, the imaginary term will become 0. So at what frequency will the imaginary terms will become 0 for this locus of g of j omega, h of j omega? The frequency is phase crossover frequency. Okay, the frequency is phase crossover frequency. So at phase crossover frequency, this whole imaginary term should become equal to 0. So let's go to the next slide. So at omega equal to omega pc, this is our imaginary term in the above equation. Equate it to 0 and simplify it. Okay, equate it to 0 and simplify it. So 9 instead of omega, write omega pc. Instead of omega, write omega pc. Okay, so what is it? 9 omega pck into 1 minus 0.5 omega pc square. Let me check whether I'm online or not. Okay. Okay then. So omega 9 omega pck into 1 minus 0.5 omega pc square. I'll take the laser. Huh? Is it 9 omega pc k into 1 minus 0.5 omega pc square minus 1.5 omega pc k into 1 plus 10 omega pc square is equal to 0. So this is our imaginary term. So this imaginary term, I am equating it to 0. I am equating it to 0, just now I have already explained. So now simplify it, 9 omega pck into 1 minus 0.5 omega square. Send this whole term to the right side, so will become equal to 1.5 omega pck into 1 plus 10 omega pc square. So just further simplify, you will get 1 minus 0.5 omega pc square equal to 1.5 by 9 into 1 plus 10 omega pc square. Okay. So you further simplify, you will get 1 minus 0.5 omega square equal to 0.167 plus 1.67 omega pc square. Okay. So if you just simplify further, you get 2.17 omega pc square equal to 0.833. You do it on your own. This is simply mathematical simplification. Nothing is there. So at last you will get omega pc equal to root of 0.833 by 2.17. That is equal to 0.62 radians per second. So we have got some value for the omega pc. So write it down. Okay. So after getting omega equal to omega pc, whatever value that you have got, that is 0.62 radians per second. Substitute that in g of j omega, h of j omega equation. So in the above equation, at omega equal to omega pc, imaginary term must be 0. So you write only the real part. That is minus k into 1 minus 0.5 omega square into 1 plus 10 omega pc square minus 13.5 omega pc square k whole divided by 1 plus uh, 10 omega pc square whole square minus 9 omega pc whole square. Okay, so just simplify it. Substitute omega pc value here and simplify it and tell me the answer. I will wait for a minute. You just solve it and simplify the if you get the answer, what is our g of j omega, h of j omega at omega pc? What is it? Tell me. Just mention in the chat box. After the class, I will forward the Google form for attendance. People solve it and post the answer in the chat box. Did you complete? So you will get okay. So that is it. Okay, you will get minus 0.1667 k. So g of j omega, h of j omega. When the locus of g of j omega, h of j omega crosses the real axis, then its value is equal to what? Minus 0.1667. So in your notes, okay, in your notes, this is our real axis u. This is JV. This is JV. For what? Sorry. For what? For, where is my cursor? For G happened G of S, H of S planes. I wanted to write G of S, H of S plane. I'm unable to press my cursor hardly. If I press it, a line comes into existence. So this is G of S, H of S plane. On this, you just locate a point on the negative real axis. Okay, locate a point on the negative real axis and write down minus 0 point, okay, 1, 6, 6, 7, 6. Okay, so this is it. This point is minus 0.1667K. So draw that. Draw it in your notes. Locate this point on the negative real axis. Okay. Now we have to draw the polar plot for section C1. We have not yet done it. So we have to do that. For that, let us move forward. So if you see here, this is our G of J omega, H of J omega. Write it down as it is. G of J omega, H of J omega is what? K into 1 plus 0.5 J omega, 1 plus J omega, 1 plus 10 J omega, J omega minus 1. You can rewrite this as what? This last term. This last term in the denominator. Okay. This term in the denominator, you can write it as minus 1 plus J. This term you can rewrite in your notes. I have not written here. Okay, I have not written here, but you people write it down. J omega minus 1, you can write it as minus 1 plus J omega. Okay, so after writing that, you can replace all these rectangular coordinate terms. Where is my cursor? It is here. Now you can take the pointer. Now you can so for 1 plus 0.5 J omega, the magnitude is root 1 square plus 0.5 omega square. This is square. Okay, then I will just go back. So that only one term, it was square. It was looking like it multiplied by 2. It was looking as if it was multiplied by 2, but it was square. So 1 plus 0.5 omega whole square root of, so at an angle of tan inverse of 0.5 omega by 1. Similarly, for 1 plus j omega, root of 1 plus omega square, tan inverse of omega by 1. Similarly, for 1 plus 10 j omega, it is root of 1 square plus 10 omega whole square, and angle is tan inverse of 10 omega by 1. Similarly, for what is this term? This is So this is nothing. This you can rewrite it as what? You can rewrite it as minus 1 plus j omega. Okay, minus 1 plus j omega. So minus 1 square plus omega square root of minus 1 square. Minus 1 square you will get 1 square plus omega square is the magnitude, and phase angle is since it is minus 1 plus j omega, so therefore 180 minus tan inverse of omega by 180. Okay, so see here. Okay, this is it. So since it is minus 1 plus j omega, you will get this 180 minus tan inverse of omega by. So this is it. Now write down all the magnitudes on one side and phase angles on the other side. These are our phase angles. So write down all the magnitudes and phase angles on the other side. What I have done, denominator phase angles, I have sent it to the numerator. Okay. So I have sent all the denominator phase angles to the numerator. So now substitute omega equal to 0 and omega equal to infinity. Okay, let us substitute omega equal to 0 in the above equation. If we substitute omega equal to 0 in the above equation, you will get g of j omega, h of j omega, magnitude as k, and phase angle as minus 180. If we substitute omega infinity, then in the above equation, then g of j omega, h of j omega, magnitude is 0.05 and 0.05 k, and angle is 0 degrees. Okay, so our plot will start from minus 180 axis and it will end at 0 degree axis. Okay, so just write it down. Are you able to follow or not? You just mentioned. Are you able to hear my voice and are you able to follow? Just mention in the chat box. Okay then. So let us analyze this part, that is C1 part. So let us consider, write down the, what we used to do for the polar plot. Let us do the same thing. Let us draw a table. For different omega values, let us see how the magnitude and phase angle for this section for the given transfer function varies. So if you, for different omega values, if when omega equal to 0, okay, so magnitude, just now we have found magnitude is k, and phase angle is minus 180 degrees. And for point 1, when omega is 0.1, magnitude is 0.707 k, and phase angle minus 210 you will get. And similarly, when omega equal to 0.5, magnitude is 0.202 k, and angle is minus 191. For 1.5 omega value, magnitude is 0.083 k, and phase angle is minus 116. And for omega 2, The phase magnitude is 0.07 K and angle is minus 95. For omega equal to 5, magnitude is 0.054 K and angle is minus 43. And for omega equal to infinity, magnitude is 0.05 K and angle is 0. So by looking at this table, what we can say that the locus of g of j omega h of j omega, it will start at where? At k, k at an angle of it's minus 80. And it will end at omega equal to 0. Okay, and it will travel to the second quadrant. Why? Because we can see that we plot so the 0 degrees and 180 degrees. They will be in equal and opposition position to each other. Means they will be just opposite to each other on the real axis, isn't it? Both lie on the real axis. So the locus crosses the real axis at which point? Minus 0.167 K. So when it crosses the real axis, even though the plot starts in the second quadrant, what will happen when it crosses this real axis point? The locus will enter the third quadrant. Okay. And if the locus crosses the negative imaginary axis or positive imaginary axis, depending on that, since it is entering the third quadrant, so in order to reach 0, okay, in order to reach omega equal to 0, that's I said. So in order to reach 0, it has to definitely pass through the negative imaginary axis to enter the fourth quadrant. So finally, the locus will end at 0.05 K at an angle of 0 degrees. Okay, so let us see that plot. Let us see that plot. So simply by discussing some theory, it is of no use. And for Nyquist, this slide is not at all required. Okay, this slide which I am showing you just for analysis in order to compare it with the polar plot. Okay, so as I have already told you, it is the extension of polar plot. So you can even plot the polar plot. So no need to do this directly since you are drawing in your notes. No need to do this analysis. So simply you just go for omega tends to 0 and omega tends to infinity. Substitute these two omega values in the above equation. Determine the magnitude. Okay. And phase angle. Okay. Now let us see the plot. So this is our plot. So this point we have already located, isn't it? This point we have already located. Take the laser, it is easy. So this point we have already located, that is minus 0.167 K point we have already located. So omega will start at some point K. Magnitude is what? When, sorry, not omega, the plot will start at some point K. So you just mention somewhere some point K. Okay. And where we know polar plot starts at omega equal to 0 and ends at omega tends to infinity. So you just look at some point and you just start your plot, okay, and that plot should reach this point. Okay, it should pass through the intersection point. This is our intersection point on the real axis. So it will start and it will reach this point, and okay, it will reach this point, and since it is passing through this point, even though it is in the second quadrant here, it will go to the third quadrant. So through the third quadrant, you just locate some point, not at the origin. You locate some point because you have got some magnitude, isn't it? A magnitude at omega tends to infinity. So I will just show you. So when omega is tending to infinity, you have got some magnitude of 0.05 K. Okay. So locate that point on the axis of 0 degrees. This is our 0 degree axis. Okay. This is our minus 180 degree. This is our minus 180 degree axis. Okay. This is minus 180 degree and this is our 0 degree axis. So plot will start. Okay. So plot will start when omega equal to 0. Our angle was minus 180. So magnitude is K. Okay, magnitude is K. Okay, so plot will start here. Even though it is moving through the second quadrant, since it has to pass through the imaginary, I'm sorry, on the crossing point. Our crossing point on the real axis is minus 0.1667 K. So it has to pass through the this crossing point. Therefore, even though it has started its plot has started in the second quadrant, it will go to the third quadrant, and it has to reach the 0 degree axis, that is our reference axis, isn't it? Locate some point. So this is my point, 0.05 K point. Okay, so some point on the real axis. It need not be very nearer to the, so I'm drawing it. Okay, so let us assume this is my K point, this is K point, and this is my intersection point. So plot will start, it will pass through this. Locate somewhere, some point. We don't have scale here. So somewhere, some point, and mention it as 0.05 K. Mention it as 0.05 K. Okay. Mention it as 0.05 K, and from this third quadrant passing through the imaginary axis, end your plot at here. Okay, and mention the arrow marks. Like this you can, okay. So by looking at the plots, it seems as if, by looking at this plot, it seems as if the plot is ending exactly at the origin, but it's not ending. Actually, polar plot should always end at the origin, but we have got some magnitude here, so nearby to the origin, not apart from the origin. That's why in this diagram it is shown nearby to the origin, not exactly at the origin, but nearby to the origin, the polar plot has ended. Okay, so the polar plots, so you just look at somewhere, some points. So points are, it's a free diagram, no proper scale is, we are not taking proper scale since you people are going to draw it in your notes. Since scale is not there, so randomly you just look at on your own. So this is minus 0.166. Sorry, I am unable to write another 6. There was a disturbance. So another 6, 7, 8. Okay. So 0.1667 feet. So this is that point. Okay. I hope you are able to follow. So you can do this, nothing complicated. So at omega equal to 0, our angle is minus 180. So locate some point K. We have already located this point. Okay. And when omega tends to infinity, our point magnitude is 0.05 K. So locate that point on this axis. So you just start from one quadrant, it has to. So always remember, if there is an intersection point on the real axis, so the plot will go from one quadrant to another quadrant. Okay, the plot will move from one quadrant to another quadrant while passing through the intersection point on the real axis. Okay, so I hope you are able to follow. Still, if you have any doubts, you just mention in the chat box, or you can ask me. I will clarify your doubts. If still, if you are unable to understand what I have explained just now, you can meet me and you can ask me. Okay then. So I hope you have drawn, because I took more time to explain this. Meanwhile, you might have drawn this. Okay. So this is our C1 section. So this is our mapping of our C1 section. So let's go to the mapping of C2 section. So we know C2 section is an arc with radius r tends to infinity. Okay. So For the C2 section, S will be equal to limit R tends to infinity R e power j theta. Okay. So theta equal to what? Theta will vary from plus pi by 2 to minus pi by 2, where S tends to R e power j theta and R tends to infinity. So since R is tending to infinity, S will tend to infinity e power j theta. Means S value is very, very high. So when S value is very, very high, 1 plus st will become st. So therefore 1 plus st, it will become st. Okay. So in the given equation, S minus 1 term is there. Instead of S minus 1, you can write S. Okay. So this is it. So 1 plus 0.5 S will become 0.5 S. 1 plus S will become S. 1 plus 10S will become 10S. S minus 1 will become S. Okay. So this is it. Simply. Okay. So this equation has been modified. Why? Because R is tending to infinity. Since R is tending to infinity, S value is very, very large. Okay. So just substitute that. Simplify it. You will get G of S, H of S equal to 0.05K. Write it down. So you have got some value for G of S, H of S, that is 0.05K. Just locate it on the G of S, H of S plane. Okay. See, earlier for the previous problems, we didn't get such a point, isn't it? We just, we didn't get any specific value in the earlier case. We didn't get any constant value. But for this specific case, okay, for this numerical problem, you are getting a constant value. Okay, some constant value you have got. So that's it. So you are not going to get any counter here. Okay, so you didn't get any counter. So what can we do? We got some constant value. So look at that constant value on the G of S H of S plane. That is 0.05K. So this numerical problem is almost there are many differences when compared to previous numerical problems in this numerical problem. So we didn't get any counter for C2. Okay. So this is our C2 plane on S plane, C2 section on S plane. So mapping of C2 on G of S, H of S plane is what? You got a single point on the real axis. You got a single point on the real axis. That's it. So locate that point on the real axis. Okay, locate this point on the real axis. That's it. Draw it quickly. To complete inform. So let us proceed further. So let us go for section C3 mapping, and we already know section C3 mapping is the easiest mapping. So here omega varies from what? From minus infinity to plus minus infinity to 0. So and this locus of g of j omega h of j omega, it will be exactly inverse of the locus of your section C1. So inverse polar plot you will get, which is the mirror image of the polar plot of C1 on the respect to the real axis. Okay. So just whatever plot that you have got earlier for C1, just opposite to it. If you remember this, sorry. So if you remember, this was our plot for C1, and this is our plot for C3. Just equal and opposite. Mirror image on the real axis. Always remember C3 is the mirror image of C1 on the real axis. Okay. I didn't notice. See, for first section, for C1, you got this when omega tends to infinity, you got 0.05 K. And for C2 section also, you got 0.05 K. Did you notice that? So at the same location, you have got. So draw this mirror image quickly. That's it. We had C1 section, C2 section, and C3 section, isn't it? We had C1, C2, and C3 section. Now let us combine all the sections. I don't remember. Did I collect all the section counters? I didn't collect. So, okay, it's okay. So we have for C2 we didn't get any counter. Okay, for C2 we didn't get any counter. So I will just explain it here. See. So this is our C1 counter. Okay. For C2, we got 0.05 K. This point is 0.05 K. This point is 0.05 K. I didn't write it here. I didn't write it. So this is C1 counter. C1 counter. C2 is what? Simply a dot, okay, on the real axis, that is 0.05 K. What about C3? Just mirror image of C1. So this is the easiest plot. Okay, so it's looking like a fish, isn't it? So, fishy plot we have got for the given G of S and H of S open loop transfer function. So now in the question they have asked us to determine the range of K, okay, for which system will be stable. Okay, so we don't know the range of K, to be frank, isn't it? To be frank, we don't know the range of K. So let us see how to determine that range. So this is our plot. This, okay, this is our plot. And till now we have 2 points. We have actually one more point is there. I didn't write it. That is, this is our K point. This is K. This point is K. And this point is 0.05 K. And this is our intersection point. Okay, this is our intersection point. These 3 points we have. Okay, so let us discuss the stability analysis for this. Okay, so since we already know that if the counter encloses the -1 plus j0 in anti-clockwise direction, okay, on G of S, H of S plane, okay, so if the counter encloses -1 plus j0, okay, on G of S, H of S plane, then the system will be stable. Okay, so it should enclose the counter should enclose the -1 plus j0 in anti-clockwise direction. If that is happening, then the system is a stable system. Closed loop system is a stable system. So for that, okay, so closed loop system is a stable system. For that, so let us initially assume that this intersection point is our -1 plus j0. Okay, it is our -1 plus j0 point. Let us assume. Okay, so let us assume that this is our -1 plus j0 point. So if this is our -1 plus j0 point, okay, so then what is our k value? Okay, this is equal to -1. Then what is our k value? So our k value, so this, I am assuming -0.1667 k is -1. It is equal to -1. Then what about k value? You just simplify it. You will get k equal to 6. Okay. So what is k value? K is equal to 6. So for assuming minus 0.1667 k equal to -1, what do you get? What do you get? You get k equal to 6. K value is equal to 6. Okay, it's just an assumption. We can't assure that k value is definitely 6. So let us assume that so we have assumed already. So k value can be less than 6 or greater than 6. We can't say. Okay, k value can be less than 6 or greater than 6. We can't say that. Since we have assumed that -0.167 k is equal to -1, we have got some k value. Okay. So k can be less than 6. So if k is less than 6, then this -1 plus j0 point will shift to the left side of the intersection point. So if k is less than 6, then -1 plus j0 point will shift to the left side of the intersection point. If suppose k is greater than 6, okay, if k is greater than 6, then this intersection point, that is -1 plus j0 point, okay. So the -1 plus j0 point will shift to the right side. So initially we have assumed this is our -1 plus j0 point, isn't it? So at that, when we have assumed that, we have got k equal to 6. Now if we assume k is less than 6, then this -1 plus j0 point will shift to the left side. And if we assume that k is greater than 6, then this -1 plus j0 point will shift towards origin. So we already know higher values will be nearby to the negative real axis origin, and lower values will be far away from the origin, nearby to the minus infinity. Okay, so that's what we can say, apart from the origin or nearby to the minus infinity. Okay, so what we can say by looking at this diagram, that where is my cursor? It is here. So by looking at this diagram, what we can say that, so this -1. Okay, so when k is less than 6, okay, when k is less than 6, the intersection point, what is our intersection point? -0.1667 k. It will lie between -1 plus j0 and origin. Okay, so if k is less than 6. So if suppose k is greater than 6, okay, so this is our -1 plus j0 point. So intersection point, this intersection point will lie in between -1 plus j0 and minus infinity. This is minus infinity. This is minus infinity. Once again, I am repeating. Once again, I am repeating. See, we have assumed minus 0.1667 k equal to -1. Okay, so this point we are assuming it as -1 plus j0 point. If we are assuming this intersection point as -1 plus j0 point, then if you solve it, you will get k equal to 6. We can't say k is equal to 6. Okay, since we have assumed -0.1667 k equal to -1, we have got this value. K value can be less than 6 or it can be greater than 6. We can't say that. If suppose k is less than 6, then this -1 plus j0 point will shift leftward, left side of this intersection point. Why it will shift away from the origin? Why? Because lower values will shift away from the origin. Lower values will be away from the origin on the negative real axis. Higher values will be nearer to the origin for negative real axis. That is understood. That we already know. So what will happen if k is less than 6? Then -1 plus j0 point will be left side of the intersection point. If suppose k is greater than 6. then minus 1 plus j0 point will be nearby to the origin. That is right side of your intersection point. Okay, I hope you have understood. So if k is less than 6, then minus 1 plus j0 point will be left side of your intersection point because it is low. And if k is greater than 6, then the minus 1 plus j0 point will be on the right side of your minus 0.1667 intersection point. Okay, so why it is right side? Because higher values will be nearby to the origin and lower values will be away from the origin. That's why. That's the reason. Okay. Now, if you compare this intersection point with respect to suppose k is less than 6. Let us assume that k is less than 6. If k is less than 6, if you want to discuss anything about the intersection point, then we can say that the where's my cursor? Somewhere. Yeah. This is my cursor. So we can say that this intersection point lies between what? Between minus 1 plus j0 and origin. It lies between minus 1 plus j0 and the origin. Now, if suppose k is greater than 6, then where does this intersection point lie? It will lie between minus 1 plus j0 and minus infinity. Okay. This intersection point lies between. So let me erase all links. Okay, I will erase all links. Okay. Now, when I have assumed k less than 6, if I want to discuss anything about this intersection point, then I can say that this intersection point lies between, since I have assumed k less than 6, this point is what? It is my minus 1 plus j0 point. This intersection point lies between minus 1 plus j0 point and origin. It lies between these two. Okay. Okay. So this intersection point, it lies between minus 1 plus j0 and origin. Okay. Now, if I assume k greater than 6, then if I want to discuss anything about this intersection point, then I can say that intersection point lies between what? Minus 1 plus j0 point. This is my minus 1 plus j0 point, and this is my negative real axis. This is my infinity, some infinite point, negative infinity. Okay, so it lies between the minus 1 plus j0 and minus infinity point. Okay. So this is about the this discussion is about the location of the intersection point. That's it, nothing else. Now let us consider first of all k less than 6. Okay, k less than 6. Here I have written, of course, it is in between. K lies between 0 and 6. Okay, so if k is less than 6, so if you observe the root locus here, if you observe the root locus around this minus 1 plus j0 point, when k is less than 6, what is our minus 1 plus j0 point? This is it. So you just observe the root locus. It is in the clockwise direction. Root locus is in clockwise direction. So if the root locus is in clockwise direction, what we can say that closed loop system is an unstable system. Okay, closed loop system is unstable system. Now if suppose k is greater than 6. Okay, k is greater than 6. Okay, so what is our minus 1 plus j0 point now? This is our minus 1 plus j0 point. So if this is our minus 1 plus j0 point, just observe the counter around this point. So counter is in, so when k is greater than 6, this is my, and k greater than 6, this is my minus 1 plus j0 point. Observe the counter around it. It is in anti-clockwise direction, isn't it? The counter is in anti-clockwise direction. So we can say the system is a stable system. Okay, system is stable system. So once again I will repeat. So when k is less than 6, this point is my minus 1 plus j0 point. You just observe the counter around this point. It is in clockwise direction. It is in clockwise direction. So system is an unstable system when k is less than 6. Now if k is greater than 6, which is my minus 1 plus j0 point, this is my minus 1 plus j0 point. Just observe the counter around this point. It is in a anti-clockwise direction. So since the counter is anti-clockwise direction, system is a stable system. For which value of k? for k greater than 6. Okay, so what is the range of k now? For the range of k, we don't have any specific range. Simply, we can say that if the k value is greater than 6, it can be 6, 7, 8, 9, up to any value you wish, any higher value. For any higher value above 6, okay, of k, the system will be a stable system. Okay. This is it. Draw it. This is the complete plot for the given system. So, did you understand the stability analysis for this system? Just mention in chat box if you have understood. Did you understand the stability analysis for this numerical problem? Mention in the chat box. So, I will discuss one more numerical problem and I will conclude this topic. So, this numerical problem, it is already there and what to say, it is, I have even designed the, I didn't design, but I wrote a MATLAB program, a laboratory program for this numerical problem, which I was about to discuss in this class. So, let us discuss this numerical problem. So by Nyquist Stability Criterion, determine the stability of closed loop system whose open loop transfer function is given by g of s h of s is equal to s plus 2 by s plus 1 into s minus 1. Okay. So comment on the stability of the open loop and closed loop system. They have asked us to comment on the stability of the both open loop and closed loop system. So first write it down, write down the question. So once, let me check whether I'm online. Okay then. So this is it. This is the given problem. I hope you have written. So write down the given open loop transform. This is a very simple and easy problem. So it has a numerator s plus 2 and denominator s plus 1 into s minus 1. Okay. So by looking at this transfer function in the denominator, if you observe in the denominator, there are no poles lying at the origin. We can say there are no poles lying at the origin. So the entire right half of your S-plane will be enclosed by the Nyquist contour. Okay, the entire right half of your S-plane will be enclosed by the Nyquist contour. So this is our Nyquist contour. Draw it. So here we can see the Nyquist contour has three sections: C1, C2, and C3. For C1 section, omega varies from omega equal to 0 to plus infinity. For C2 section, theta will vary. Okay, theta will vary since it is an arc. The arc of C2 section, radius of this arc is r tends to infinity, and theta will vary from plus pi by 2 to plus pi by 2 to minus pi by 2 for C2 arc. Whereas for C3, C3 varies from omega tends to minus infinity to omega tends to 0. Okay, so we'll perform the mapping of each section separately, and overall Nyquist plot will be obtained by combining the individual sections. Okay, individually we will combine all the sections and we will plot the Nyquist plot each section. Okay, I hope you have drawn it. So now mapping of section C1. So section C1, omega varies from 0 to plus infinity. Okay, omega varies from 0 to plus infinity. So consider the locus g of j omega, h of j omega, where omega varies from 0 to infinity. So what you have to do is simply take g of s, h of s, and since it is in the form of s plus 2, s plus 1, s minus 1, convert that into 1 plus st form. So you can easily convert it. You just take 2 common in the above equation, 1 common here, and of course for this nothing. There's no need to take common. Simply just shift their positions in the denominator terms. In the above term, you have to take 2 common, and you will get 1 plus 0.5s. 2 into 1 plus 0.5s, and the denominator simply shift the positions of 1 and s. 1 plus s you will get. Simply change the position of second term 1 and s, that is minus 1 plus s you will get. Okay. So g of s, h of s, we have got the whole expression in the form of 1 plus st if there are denominator and numerator first order factors. Okay. So this is it. This is it. This is the equation. Now replace s by j omega. So you will get g of j omega, h of j omega. Okay, that is equal to 2 into 1 plus 0.5 j omega by 1 plus j omega into minus 1 plus j omega. So just write it down. Okay, then I hope you have written. Now, simply what are expression that you have got, I have rewritten in the second slide, and I have determined the magnitudes for each and every factor here and phase angle. So for 1 plus 0.5 JMV, you will get of 1 plus 0.5 whole square, and magnitude and angle tan inverse of 0.5 omega. For 1 plus j omega, you will get root of 1 plus omega square, angle tan inverse of omega. For minus 1 plus j omega, you will get angle 180 minus tan inverse of j omega and magnitude root 1 plus omega square. So you just write down the magnitudes and the phase angles for each and every term. Okay, after writing magnitudes and phase angles, write down all the magnitudes on one side and phase angles on the other side. Okay, so I have separated the magnitudes. This is the magnitude of j omega, h of j omega, and this is the phase angle of g of j omega, h of j omega. So we have magnitudes and the phase angles. So we can plot the polar plot actually with these magnitudes, and we can get an exact plot for the Nyquist for section C1. We can get the exact plot, but of course we are not going to plot the graph on the graph sheet. So polar plot on the graph sheet, so no need. Okay, I hope you have written this. So here, in order to get the exact polar plot, if you want to plot the exact polar plot, so you consider different omega values 0, 0 0.4, 1, 2, 10. Randomly, you can consider any values. Okay, but make sure, since you are definitely for polar plot, initially it should be 0 and at the end there should be infinity. So for 0, magnitude is 2 and angle is minus 180. This is important for Nyquist plot for us, since we are going to plot the graph on the notes, in the notes. So for 0 0.4, magnitude is minus 1.76, sorry, and angle is minus 168. And for 1, omega is equal to 1, magnitude is 1.12 and angle is minus 153. For omega 2 and magnitude is 0.57 and angle is minus 135. For omega 10, magnitude is 0.1 and angle is minus 101. For omega equal to infinity, magnitude is 0 and angle is minus 90 degrees. Okay, so this is it. So you can get the perfect plot if you consider the different omega values and different for different magnitudes and phase angles. You will get a good plot, but it's not required. So just consider. Cursor. Yeah, just consider this section and this to plot the Nyquist plot. So for omega tends to 0, there is my cursor. So for omega tends to 0, magnitude is 2. In which axis? Minus 180 degree axis. For omega tends to infinity, magnitude is 0 and angle is minus 90 degrees. Okay, so let us go to our plot. So this is our minus 180 degree axis. Okay, and this is our minus 90. Sorry, minus 90 degree axis. Okay. This is minus 90, this is minus 180. So our plot will start. Magnitude at minus 180 is what? it is minus 2, and at minus 90 it is 0. So as omega varies from 0 to infinity, okay, so 0 to infinity, so you will get this plot. You will get this plot. This is it. This is our mapping of section C1 for G of S, H of S plane. Okay, so mapping from S plane to G of S, H of S plane. So one thing that comes to our mind is that, so instead of plotting in this quadrant, we can even plot this in this quadrant, isn't it? Okay, we can do that, but it is minus 90 here, this is minus 180 here, so definitely the plot should go in this way. If you still have doubt, what you can do is, for what I have done in the previous slide, for different omega values, determine magnitude and phase. Okay, and if you observe, all the angles are negative, isn't it? All the angles are negative. Okay, so definitely it will, you have to plot like this. Okay, it depends on which axis it is about to start and which axis it is about to end, the plot. Okay. So draw it. Okay, then this is our C1. Let's go to mapping of section C2. So mapping of section C2. So here, and for C2 is an arc. So S will vary from limit R tends to radius of the arc is infinity. So limit R tends to infinity, R. So this bracket is not there. So this is it. Okay, now. So here S is equal to R tends to infinity, limit R tends to infinity, R E to the power of j theta. Okay, where theta varies from where? From plus pi by 2 to minus pi by 2, where S tends to R E j theta and R tends to infinity. So as R is tending to infinity, S will tend to infinity e power j theta. SL is very, very high. So 1 plus ST. 1 plus ST, you can replace it by ST. So consider your given open loop transfer function G of S, H of S. Okay, and it just replace 1 plus ST by ST. So 2 into 1 plus 0.5 S. So you can rewrite it as 0.5 S. And 1 plus S, you can write it as S. Minus 1 plus S, you can write it as S. So this is it. You just simplify, I'll get 1 by S. So G of S, H of S is equal to 1 by S at what? At S is equal to limit R tends to infinity. Okay, R tends to infinity. Here R should go. R tends to infinity. R e power j theta. This is it. Just write it down. Write down the equations. Okay, so now substitute the limit terms g of s h of s at s is equal to limit r tends to infinity r e power j theta. Just substitute here. In 1 by s you will get 1 by limit r tends to infinity r e power j theta. Once again. So here it should be 1 by s. The equal should be there, and here it should be 1 by s. 1 divided by s should be there. At s tends to this is it. This is how it should be. So now if you substitute the limits, if you see 1 by limit r tends to t r e power j theta, substitute this 1 by infinity, you'll get 0. 0 and 1 by e power j theta, you can write it as send e to the numerator, you'll get 0 e power j theta. So what is happening now? This g of h, g of s, h of s, g of s, h of s is equal to what? 0 e power j theta. Now substitute theta values. We know theta varies from plus pi by 2 to minus pi by 2. Substitute theta values. If we substitute theta values, g of s, h of s will be equal to 0 e power minus j pi by 2. And g of s, h of s will be equal to 0 e power plus j pi by 2. Just note it down. Just mention in the chat box. Are you able to follow or no? Okay then. Now this is our radius 0 and theta is varying from minus pi by 2 to plus pi by 2. So our actual plot on S plane was C2 with radius r tends to infinity. Now our radius is what? R tends to 0. What is our theta value? Earlier it was theta was varying from plus pi by 2 to minus, sorry, minus pi by, okay, theta was varying from plus pi by 2 to minus pi by 2. Now theta varies from minus pi by 2 to plus pi by 2 with radius 0. Okay, with radius 0. So earlier it was varying from plus pi by 2 minus pi by 2. The counter was in clockwise direction. Now it will be in anti-clockwise direction from minus pi by 2 to plus pi by 2. So this is our counter. So, counter of section C2 on G of S H of S plane. Counter of section C2 on G of S H of S plane. Okay, plot it. Okay, now let us go for the mapping of C3. So where C3, so mapping of C3. So for mapping of C3, omega varies from minus infinity to 0. So as omega varies from minus infinity to 0, okay, so it is just the mirror image of C1. So you will get an inverse polar plot on the real axis. So whatever plot that we have got earlier for C1, if you see just opposite to it, you need not do anything. Just opposite to it, you just draw the plot. So this is our C3 S plane, C3 on S plane, and this is our G of S, H of S plane C3 counter. Okay. Now we have got all our three counters, so we can combine them together. Okay, so if you combine them together, so for all the three contours, if you combine them for all the three sections, if you combine them, you will get this. So this is our C1 section contour. This is our C2 section contour. This is our C3 section contour. This is C1 section contour. This is C2 section contour. This is C3 section contour. So combine all the contours. Okay. So what is this point? This is -2 point. Okay, this is our origin. And we already know this is -2. Definitely -1 plus J0 should lie in between -2 and origin. So let us see the stability analysis of this. Okay. So definitely in between these two, the -1 plus J0 contour should lie, point should lie. So if we observe the contour around this -1 plus J0, the contour is in anti-clockwise direction. The contour is in anti-clockwise direction. Therefore, so the number of anti-clockwise directions around the -1 plus J0 point will show us how many poles are lying on the right side of your S-plane. So there will be one pole lying on the right side of your S-plane. If poles are lying on the right side of S-plane, then definitely open loop transfer function will be an unstable system. Okay, open loop system, not open loop transfer function. The open loop system will be unstable, whereas closed loop system will be a stable system. Okay, since there is an enclosement of this or enclosement, or what we can say, since -1 plus J0 is enclosed, since -1 plus J0 is enclosed one time in anti-clockwise direction, therefore closed loop system will be a stable system. Okay, closed loop system will be stable system, whereas open loop system, it will be an unstable system because one pole will lie on the right side of your S-plane. So our result is open loop system is unstable, whereas closed loop system is stable system.